Hello? Hello? Can you hear me? No? We'll just go with this. Can everybody hear me okay?
Yes.
All right, I will do my best to stay loud. If I'm not loud enough, please just jump up and down and I will adjust. My name is Tim Fishman, isn't it?
Yeah.
Oh, you can do this, it's fine. My name is Tim. I work in Kubernetes at Google. I'm one of the original Kubernetes team, the first four, I like to say. I'm going to talk today about what's going on in Kubernetes. We are about to cut our third major release, and the request for the topic today was, let's talk about what's new. So, who's looking for Kubernetes 101? Yeah, you're in the wrong room. I'm happy to talk more about the basics. I've got a ton of cool demos I would love to show you after. I only have 30 minutes, and I have about 150 slides, so I think I'm kidding. So I'm going to race through the most important, newest topics going on. I do apologize, guys. Come see me afterwards. I'm happy to show you the basics, answer questions later. In the same vein, let's save questions for the end, unless it's like absolutely dire critical, then we can go for it. And at the end, I say, get me in position. So, just a quick obligatory introduction to Kubernetes. It's a cool word. It's actually the root word of the word governor and the root of the word cybernetic, which has nothing at all to do with why we chose it. It actually means the guy who drives the boat. We love the Docker theme of shipping and nautical, so we stuck with that. So, containers and clusters. Kubernetes is all about container clusters. I want you to put those words in your brain. Container cluster. What is a container cluster? It's really two parts. The first part is setting up a cluster, picking which cloud you're going to run on, knowing what sort of things you're going to do with clusters, setting up the networking. This is hard. Right? This is terrible. If this is your first experience with Kubernetes, you're going to sort of hate it. It's unfortunate, but you got to go over that home. Then you get to the second part. The second part is the fun part. This is sexy. It's all about using the cluster, running your containers, scaling dynamically, watching what happens. This is the fun part. This is what I'm going to focus on most of today. I'm happy to talk about how to set it up, how to get your network working properly. You're working desperately to make all that stuff easier and more streamlined. The fact of the matter is, in the end, you have a bunch of machines and networks and storage and that else. So we're going to talk about this part. So I'm going to talk specifically about stuff that's new in our newest release. So the first thing I want to talk about is services. Services is an abstraction of Kubernetes that is essentially of linking together. This is not a new concept. This is a Kubernetes from the very beginning. What I want to talk about is this, the idea of Kubernetes virtual IPs and our built-in load balancers. We have a new version of our kube proxy, which is the thing that implements our virtual IP. So the new version, so we came out with Kubernetes, the first version, and we had our first our proxy. And man, did we get beat up. It's sort of slow, it uses a lot of memory, occasionally it leaves sockets, it bounces everything through user space. It's, you know, it was incredibly painful. But it was great for a first version. So we've rewritten it. The new version is 3 times faster, has no leaking problems, has no client IP obscuring problems. So
sorry, I need to switch.
It's written in Go, but the new version never touches your packets. The new version just configures the kernel to get all of your packets routed the way we want it, and then it gets out of the way. So none of your traffic will actually transit through user space. So go back to the first slide there. All right, go on. I'll explain to you guys later how it's working. So kube proxy is a little agent that runs on every machine. It watches our API server. It says, hey, API server, tell me whenever there's a service object, the capital, should be a capital S, or an endpoints object on the server, tell me when that changes. So the user comes along and says, I want to run something. The user says kubectl run. Now, what happens when a user says kubectl is our command line tool. When the user says kubectl run, we go out and we schedule some jobs. See this little icon? This is a job. This is a pod. So get used to that icon. Because that it schedules these things. Now the user says, I would like to take those pods and I would like to make a service on them. I want you to give me a virtual IP and a virtual load balancer that fronts all of these services. So the user says kubectl expose. The API server updates our kube proxy and says, hey, there's a new service. So the kube proxy then reaches out, configures IP tables, which creates a virtual IP that points nowhere. There's no backends for this service yet. Now the API server says, oh, by the way, you also have some endpoints for this service. So again, we go out and configure IP tables. We throw in a randomizer in the front, so you're going to get some random probabilistic access to your backends. Now, along comes a client. Well, a client wants to consume this service. The client accesses this virtual IP, which gets translated, put through the randomizer, picks a backend, and your traffic is sent. If you knew anything about Kubernetes, the first version, what would actually happen is we'd copy it out to user space, we'd make a new connection for you, we'd add an entry to our table, we would then lose your client IP because there's really no way to pass it down to the backend, and it was really sort of awkward. The backend sees your client directly, right? It's actually incredibly performant, and it works really, really well. Along with this, we have a concept called external services. External services let you take a Kubernetes service. This again has existed for a long time. Takes a Kubernetes service and exposes it on a load balancer. If you're running GCE or AWS, you get a cloud load balancer configured for you automatically, and now your service is published to the internet. So what's new is this new object called Ingress. Ingress is an L7 load balancer, which you can now set up on top of services, and you can configure it in all the ways you're used to with an L7 load balancer. You can have host mappings, you can have URL path mappings, you can have TLS, which is new in this version, and you can use an arbitrary set of backends. These are runtime plugins. If you run on GCE, you're going to get the GCE plugin by default, but you don't have to use it. You can replace it with HA proxy if you prefer HA proxy. Likewise, AWS or Nginx, and people are writing more and more of these Ingress plugins, which is just fantastic. So this is a beta product in Cube 1.2. We hope to expand it to cover things like SNI and L4 TLS. That's why we've left the beta for now. All right, next topic is my favorite feature of Cube 1.2, something called a config map. A config map, let's go back to the root of these problems. Who's read the 12-factor docs? Who's memorized the 12-factor docs? Which factor is that your config should come from the environment? That's like number 2 or something. It's really important. 12-factor says bring in your configuration from your environment. Don't build it into your application, right? The environment is Kubernetes. So how do you use Kubernetes to get your configuration injected into your application? So we now have an object in our API called config map. And config map is really a map of string to string. Specify a key and a value, and we'll feed it into your application at runtime. What's cool about this is it's late binding, so you can update your config map right up to the time you run your containers. And when you run your containers, we will actually project it into the file system for you as files, so you can then access it. If that's your SSH key or if that's a config file, we can just inject it straight into your application. If you want to update your configuration, you can go update it live on the fly, in which case we will actually update it atomically for you in your container, or you can create a new config map and do a rolling update and you get your new version. So it's up to you to manage how you want to do your updates, but you have the capabilities to do this live. Unfortunately, I cannot do a demo of this because the final bit of user experience part of this is not done. So it will be generally available, GA, in Cube 1.2, which is due to come out in a few weeks. It is done. This is an amazing feature. It's so simple, but it makes things so much better for everybody who's asked, how do I configure my Nginx? How do I inject stuff into my application? All right, very closely related to config maps is something called secrets. Just like config map, you don't want to inject passwords and those sorts of things into your application or into your containers, because as soon as that changes, you have to redeploy your applications, right? This is the sort of thing you want to inject from your environment. So secret is like config map, except it's specifically targeted at storing things like passwords. So again, you can configure your containers to run, and we will inject your passwords as files into your file system. So I'm going to do a quick demo here. I swear that all these demos are live, they're really running against my cluster. I just have them auto-typing because I cannot type in front of people. Well, the first thing I'm going to do is show you the YAML that makes up a secret. And what you see in here is a very simple YAML object. The top is our sort of boilerplate Kubernetes that identifies what it is. And then you have type is opaque. This is not a type that Kubernetes knows anything about. And the data is base64 encoded so that I can stick some binary stuff in there if I need to. And so I'm going to go ahead and in my demos namespace, I think I forgot to create the namespace. Darn it. First things first, let me create my namespace so that I can play with all this stuff, make a big mess in my cluster, and then throw it all away. So what you see right now, there is no namespace called demos. So I'm going to go off and create a namespace. Here's another block of YAML. Now you can see I have created a namespace called demos. It is 3 seconds old. Let's run through secrets again. So there's my secret YAML. I'm going to kubectl create the secret. It has been created. Now I'm going to run a pod. So here you see a pod. A pod is our what we call a group of containers that runs together. The interesting part here is I have a volume mount that is called my password, and I'm putting it on /data. And the volume is named my password to match. And it is a type secret, and the secret name is my secret password. My secret password is the object I just created. So I'm going to go ahead and run my pod. The pod has been run. I'm going to make sure that it's there. It is in fact running. So I'm going to exec into my running pod. So I've actually just made a connection through our API server to the running pod in my cluster on GCE from my laptop right here. And what you'll see is I have those files, password and username, that were base64 encoded in my secret object. And I can, whoops. This is why I don't type in front of people. You can see that my username is there, and my password is there. And this gives you the ability now to, with your own applications, inject your configuration at runtime. If you decide you need to rotate your keys, it's as simple as restarting your applications, and the secrets get changed out. Let me flip back to slides.
Is this new in 1.2?
This is not new in 1.2. I wanted to talk about it because it was new in 1.1 and it was something that I didn't cover very much in these sorts of talks. And because it's related to config map, I wanted to sort of show it off. Right, moving on. All right, next. So anybody who's played with Kubernetes, who's done the rolling update, who's walked through that demo, it's a pretty cool demo, right? So rolling update takes a set of pods that are running and it moves into a new version all live while the whole system is running without any downtime, which is super cool, except at the end of a rolling update, you have changed your application controller from version A to version B. You've got a new object with a new name. It's sort of obnoxious and it's sort of tedious. And in fact, Kubernetes, we don't like imperative. We don't like being told what to do. And when I say kubectl go do a rolling update, that's sort of an imperative operation. So we decided we needed a declarative way to say what I want. This is a deployment. A deployment lets me say, this is the state that I want, make it so, right? We wanted to call it kubectl make it so, but we thought it was too cute. What it really lets you do is you have a single object that has a stable name and a stable identity in the system that you can then edit, apply, patch any of our existing mechanisms to change that object, and it will deploy the thing for you. And it will do the rolling update as a service, and it will aggregate your statistics, et cetera, et cetera. So let's do a quick demo of a deployment. This is a new demo, I hope it works. So here's my deployment object. Sorry, first I'm gonna create a service object. The service object is gonna front my deployment so you can actually see that the switchover is making a change as I go. So we've gone ahead and created the service. So I'm going to deploy version 1 of my application. It's a little big for the screen, but what you see is I have 3 replicas, and the template pod is called demo. It has a label demo deployment, and it's going to run a BusyBox container. And all the BusyBox container is going to do is echo the date and the string v1 into a file and go to sleep. So it's going to do this. Meanwhile, it runs a second container, which is just an Nginx server, which is serving that same file. You can see the volumes, you might share the same file. Oh! Oh, I killed it. Well, there you go. It's proof that it's a live demo. All right, I'm not going to debug it live. Let's just move on. Rest assured that this morning it worked. This is what you get for live updating your cluster the day of your demo. So what would have happened is you would have seen version 1, and then I would have done a deployment update, and I would have substituted version 2 for version 1, and then it would have switched over from v1 to v2, just like the rolling update demo, except I don't have anything running in my command line on my client side. I can take my hands off the keyboard and let it run. I apologize for that demo not working. I'll fix it and show you later. Keep me moving, Vish. That was pretty cool. I bet you can't do that on purpose. So this is a, sorry, go back one. This object is beta in Kubernetes 1.2. It is going to be the foundation of a bunch of stuff that we do moving forward in making our cluster turnups simpler. This is going to be a way that we make all of the things that we do ourselves even easier.
Question, are you going to provide an API for us, the rolling update that we don't really have?
The question is, are we going to provide an API for rolling update? Sure, there's an API for rolling update. The API is bring up a new job and delete an old one, right? The problem with providing an API for something like a rolling update is that whatever API I provide you is not going to work for him. And whatever I provide for him is not going to work for you, and whatever I provide for them is not going to provide for them. Our experience in Google is the updating of an application is very specific to the application, and trying to make a works for everybody, sort of one size fits all rolling update just is a doom to failure. So what we've provided is a very simple way of doing a rolling update. If you need to do something that's more custom than than what we do with rolling update, what we do is literally about 50 lines of Go code, and that's because we have error checking and stuff. If you've written Go, it's about 2/3 of your code. You can take it and do your own. You can change the policies to be how you want. You can change the timeouts. You can change the checks that go in between the updates. All of what we're doing with rolling update is built on top of our public API, on top of pods and services and replication controllers. There's no secrets. There's no backdoors. It's something that anybody can replace if they don't like what we're doing. So the next object I want to talk about is called job. So Kubernetes from version 1 has always been about web services, things that run forever, right? If you wanted to run a job that ran to completion, we didn't have really good support. Now, what sort of stuff would run to completion? I don't know, maybe like Hadoop, right? All the big data work, all of the analysis that people want to do, like 2/3 of the compute that actually happens in the world is sort of run to completion work. So we finally have support for Java. What Java allows you to specify, it's sort of like a replication controller. You specify how many copies you need to run, but it lets you differentiate how many do I want to run in parallel and how many do I need to actually complete for this to be considered a success. If something fails, what do I do with it? I can either restart it if it fails, for example, like a workflow where I need an image processing algorithm to complete, or maybe I build my compile farm on top of this. And if it fails, it's probably not going to complete the next time either, right? You forgot your semicolon. So we have an option of what termination modes do you want. Again, it aggregates success and failure counts. This is built for big data and batch work. Hit me with the demo. All right, so again, here's a job, and it's a very simple container. All this container is going to do is sleep for 5 seconds, pull a random number. 1 out of 4 times the random number is going to be 0, and it's going to exit with failure. Right? That's all this job does. I'm going to demand that it runs 15 times, and that it can run 5 at a time. So I've created my job. Let's look and see what we did. So I run describe jobs. And it's showing me, you can see here, 5 running, 0 succeeded, 0 failed. You can see all the pods that are running for it. This is just going to run in a loop. So there's my pods that are running. And we'll run the describe again. Oh, it's not cool. Hold on. Here you can see 5 running, 7 succeeded, 4 failed. We'll run this in a loop until we hit 15. It doesn't matter how many fail. We'll just keep trying. $13 succeeded. Ooh, 11 failed. Man, the random numbers are against us today. At first I had it failing 50% of the time, and it seemed like it was too much. So you can see here the final status that, of all the jobs that we ran. If I felt so inclined, I could go and get details about all these ones that failed with an error. I could go see what their termination message was. I could go pull their logs. I could look at their status codes. Whatever sort of artifacts came out of this, I could retrieve from here. But now my job is done. Take me back. All right, the next cool, yes, question.
What's the exit code supported? 0, 1?
0 is success, anything else is not.
Okay.
Just like Unix. So the next cool feature I want to talk about is horizontal auto scaling. Right? This is it. This is the holy grail. I want a job to run, but I don't know how many copies of it I need to run. So HPA, horizontal pod autoscaler, will automatically scale a replication controller based on CPU utilization. And I believe they've actually already added custom metric support. So you can actually scale it based on metrics that come out of your own application, QPS or whatever you need. You give it a min and a max number of copies to run, and it will manage it based on that. So set it, forget it. This is also a GA feature in Kubernetes 1.2. Get me back to my demo. So I'm going to run this is awesome. I'm going to run a pod. I'm setting its limit to 100 milli-CPUs. And I'm going to, all this pod is going to do is sleep for 5 seconds, and then it's going to run yes. Who knows what yes does? It eats CPU, right? This is all it's going to do. So now it's running. Oh, maybe already too late. I talked too long. So you can see that it's up and running. It's got 1 current, 1 desired. Oh, sorry, that's the replication controller. Now let's create an autoscaler for it. No. First, I'll convince you that I ran 1. So this is I seeded it with 1 job, right? I'm running my web server. I don't know what's going to happen. Maybe I'll be successful. Maybe I won't. I'm a startup, right? But I'm going to go ahead and plan for success. So I'm going to set up my autoscaler. I'll set it to only allow up to 10 copies. And you know what? If my CPU goes above 25%, I want you to start bringing on more copies. So now it's going through the initial stats gathering phase. It's got to wait, on the order of a minute for some stats to come in to understand what exactly is going on with my CPU. In the meantime, that one little pod is chewing away on as much CPU as I've let it have, which is 0.1 CPUs. So you can see 1 pod. No, we still don't have stats. So meanwhile, what's going on here is it's going through yet another API, which I'm not demoing in first class, which is our metrics API. And it's gathering statistics and saying, given your limit, how much CPU are you using? And figuring out over time, it's doing some analysis to figure out if it's time to scale this pod. Oh, of course, it's going to take a while today. Oh, there it goes. Now, because I was so aggressive with the limit, it's probably going to go straight to 10. Yeah, see, I'm at 996% of CPU, and I set my threshold at 25, so it's already jumped from 1 to 10 that quickly, right? And if I had some way to dial down the CPU on those pods, which I don't, then you would see it start to drop, but it will drop a little bit more slowly than it went up. And again, that is GA in 1.2, so that's there and ready for you to use.
Can you talk about how you pick which pods to kill?
The question is, how do you pick which pods to kill? And the answer is sort of random, but it's not truly random. We'll actually pick any ailing pods first, so anything that's marked as not ready, we'll choose to kill before we kill anything that is ready. But once we get to the ready phase, I'm pretty sure that it's just a random number. Next slide. All right, last thing I'm going to demo today, and then I will give up the stage, is something called a daemon set. So like a replication controller, a daemon set runs a number of pods for you. The difference here is daemon set says, I'm going to make sure you run one per machine, at most one per machine. What it actually lets you do is select which nodes you want to run on, and then run the job on all those machines. So for all of you who want to run some piece of infrastructure, you want to run it on every machine in your fleet, but you only want to run it once, this is what is going to guarantee you that ability. And this is a beta object in Cube 1.2. Bring me to my demos. So the first thing I'm doing is I clean off all the labels on my nodes to make sure the demo works. And I will show you that there are no labels that matter. Specifically, I'm going to base on the color label. So if you could look through this map, you'll see that there is no color label. No tricks up my sleeve. So first things first, run a service that's going to front any daemons that I end up getting created here. Okay. Now let's run our daemon. So here's the YAML for our daemon set. What I'm running here is a container called serve hostname. All it does is serve its hostname on HTTP. It is going to only run on nodes that are colored red. Right now there are no nodes that are colored red. So let me go ahead and create that. Just to show you that it's there. There are, it currently thinks it should have 0, and it has 0, so it's happy. All right, so on this side, I'm just going to curl the service. And what you should see for a while is some timeouts because there are no colored red daemons around. And then on the right side, I'm going to actually go through one by one on those nodes, and I'm going to color the nodes with an annotation. I'll label that. Oh, and there it goes. It popped up on the first node. Now we've labeled the second node. And there, now you're seeing the mix of them coming through the surface load balancer. Remember that randomizer I drew up before? This is the randomizer that you're seeing there now. And then I went through and I hit the third node, and now you should see some random mix of all 3 nodes coming through my service. There you go. There's at least 3 up there. Back. All right, I'm going to wrap it up now. So who's hopelessly lost? Come on.
Good.
Oh, good.
Why don't we combine this with the replication controller?
So the question is, why don't we combine something like daemon set and replication controller? Part of the ethos of Kubernetes is small domain-specific objects. We would rather have 100 objects that do one thing well than 5 objects that do 20 things. So we've already, for example, built a second-generation version of replication controller called replica set. It's not really ready for use yet, but the idea was we learned some lessons through replication controller. We're fixing them in replica set. It's a one domain object. If it had 15 bits of functionality, it would be that much harder to replace and that much more dangerous. Yeah.
I noticed when you were filming the job set, if you were able to see all the pods created by that job set and those resolved the logs. You can't do that today with a replication controller. Like it, the pod dies multiple times, sort of the previous sort of instances are wrong, so you can't check the logs that you can with that job.
So actually, I pulled a trick on you. You can with a replication controller. There's a special flag kubectl that will show you terminated pods. And so if you had something that had failed and been restarted, the -- show all flag will actually show you things that have been terminated. They're there, they're just hidden. Garbage collection is much, much slower than that. Yeah.
The yes job that actually you ran, in the CPU utilization actually shows like 960%.
Yes.
How is that possible?
So the question was, the yes job showed 990+%. Because I was running 10 pods at 100% CPU, so 10 times 100 is roughly 1,000, and I had set my threshold to be 25%. So it's a little weird in that display that you see the aggregate CPU usage compared to the per pod CPU usage. I noticed that now that you pointed out, but the reason was I had 10 pods running at 100%.
So basically that is translating into how many more nodes you have to add, or
That's
CPU to add more.
If I didn't put a limit on it, it would keep adding replicas, not knowing that each replica is going to actually make the problem worse, which is actually a real problem. We've never experienced that. It would just keep adding replicas until it tried to get the CPU down below 25% on average. Yeah, question?
That was firstly a cool demo. And secondly, are you planning to post your demo scripts and slides to GitHub?
The demos are already on GitHub. They're currently in my personal repo because I haven't gone through the process of like putting them in the Kubernetes repo. But if you find me on GitHub, they're called Kube demos. You can get them, and there's a README that'll tell you how to get the self-typing stuff and everything. And they are really running against my real cluster right now. I promise. Hit me. We're done. So let me wrap up. Skip this. Persistent volumes will now auto-provision. Network plugins. Keep going. You thought I was kidding, but I had 150 slides. So here's just a list of more stuff that I couldn't demo today because we just did too much cool stuff in this release. This is all stuff that's in the current release. Multi-AZ support, which has been long in the tooth. Multi-scheduler support, node affinity. These are things that a lot of people have asked for. These are now part of the system. We will now scale to 1,000 nodes. We'll put 100 pods on every node. Put that in Python Smoke. And then over here is stuff that's coming up in future releases, stuff that's already in progress. Just tweeted today from the wonderful folks at Calico, who I know are sitting in the room, is network policy microsegmentation. We finally have agreed on a schema for the prototype of that, and the Calico guys already have a demo online, which is pretty freaking awesome. Hold questions until I'm done, please. Here's the status and plan. So version 1.2 coming soon. The plan is early March that we will have a 1.2 release. We've got all of these cool things that are building on top of Kubernetes. We're trying to hit our 3-month release cadence. Go ahead, just jump ahead. Last reminder, Kubernetes is open, 100% open. We do all of our design in public. We do all of our discussion in public. We have special interest group meetings every week, and they're all on Hangouts, and they are recorded, and you can come and watch them and join them. You can jump on Slack and come talk to me. I'm on user support tomorrow. Come and beat me up. All of the code is there. We depend on community to make this thing happen. We crossed the 20,000 commit mark, or 20,000 pull request mark last month, which is pretty staggering to me. And it's just getting faster and faster on every single release. So, and that's possible just because of people who use it and try it out and find bugs in it and file them and fix them. And I am incredibly awed and wonderstruck at the community that we built. That's it. I literally have 120 more slides that I can go through if people want to talk about them afterwards. Let me take a couple questions real quick. I know you can dive into the other questions. Thanks.
Yeah. So what are you trying to do with big data?
What are we trying to do with big data? The goal is to make the whole process more streamlined. I'm a little tuned out from that effort. It's actually happening mostly out of our Seattle office, and I haven't checked in with them in a couple of weeks. But the goal is to make it as easy to run Hadoop or any of the other big data systems on top of Kubernetes as it is to run on top of Mesos or the other big data systems. It should be first-class support. There should be nothing between you and doing your big data analysis.
What do you use Kubernetes internally for?
What do we use Kubernetes inside Google for? Mostly we don't. Kubernetes is inspired by Borg, but Borg is 14 years old. It has a lot of features, and a lot of them are really bad. A lot of them are things that we added and now wish we could just get rid of, but we can't because people are using them. So the lessons that we take away from Borg are feeding into Kubernetes. But Kubernetes is just too young to use inside Google. It doesn't have enough features. It's not crazy enough. And frankly, we have Borg, right? So until Kubernetes offers a value prop that surpasses Borg, it's going to be a really hard sell to convert all of our 100 bazillion machines in Borg over to Kubernetes. Don't get me wrong, I am working on it, but it is a multi-year plan. We'll take the last one in the back, and I'll take the rest after.
Why do you draw the line between Kubernetes and Mesos?
Why do I draw a line between Kubernetes and Mesos? I just drew it as a comparison for this, for big data. Big data and Mesos is well known, right? Mesos is pretty well understood to have very good support for big data through the verticals of Spark and those sorts of things. And we want to be just as easy as that, right? We want to be as well known as that. I'm going to have to take the question backwards. I know I'm over time, so I'm respectful of the next guys. I have stickers. Please come and see me afterwards, and I'll be happy to answer questions. If you really are hopelessly lost here, I can go all the way back to the very beginning and do the very first demo to show you how the fundamentals work. I'd be happy to take questions or talk stories afterwards. Thank you.
All right, great. I'm just going to jump right in. Yes, we're all good to go. All right, great. Let's jump right in. My name is Chris Marino, and I'd like to spend about 10 minutes with you tonight, 10 or 15 minutes, talking about some of the new enhancements that are available coming up in Kubernetes version 1.2 that support multi-tenant and policy-based networking. And then I'd like to pass it over to my colleague Robert Starmer, who will give us a live demo of Kubernetes running version 1.2, and he'll show some multi-tenant networking and apply network policy using a new software-defined networking solution called Romana. Can you click forward, Robert? Thank you. So very quickly, the agenda, I'm going to talk a little bit about something that we've described as cloud-native networks, and they really are an effort to identify the unique requirements of cloud-native applications and design networks around those requirements and solutions that actually are able to automate and provision those types of networks. I'll talk about a new open source project that we just launched last week called Romana. That's a software-defined networking solution that actually allows you to automate the provisioning and control of these cloud-native networks. We'll go into some fairly low-level detail on how it all works, and then I'll pass it off to Robert for a demo, and hopefully we'll have time for a Q&A, although I'll try to make up a little time because I know we're running a bit late. Okay, next slide, Robert, thanks. Okay, there's a lot going on here, and I'm really just sort of cut to the goal line. One of the reasons why virtual networks are so complicated is because they try to recreate enterprise networks, and they do that through basically what amounts to LAN emulation. And LAN emulation fundamentally requires layer 2 networks, or VLANs. And I could walk through a very detailed analysis of why that's the case and so on and so forth. You can go to romana.io, you can see all sorts of information on why that's true. But let me just cut to the chase here. Cloud native networks don't need layer 2 networks. You go to the requirements of Kubernetes, requirements for cloud native applications, all they need is a reachable IP address. That's it. So what we've come up with is a solution that allows the creation and provisioning of networks that just give you a reachable IP address, nothing more, nothing less. So it vastly simplifies all of the requirements for the networking solutions, and I think most people here are probably familiar with some of the struggles that come along with container and cloud-based networks. So that's the good news. The good news is cloud-native networks don't need layer 2 networks. And because of that, a lot of the complexity of virtual networks just melts away. It just disappears. The bad news is layer 2 networks were a very convenient and very simple way to provide isolation among applications and tenants. So that's one of the reasons why layer 2 networks were brought forward into virtual networking, because it provided it was almost like a crutch to provide an isolation mechanism for virtual networks. So let's click forward, Robert, thanks. So what cloud native networks are and what cloud native SDN is a way in which to provide the isolation that you would ordinarily get with layer 2 networks, but do it entirely at layer 3. And the way we do that is the way networks have been isolated and provisioned literally for decades, and that is simply by assigning IP addresses to dedicated purposes. I mean, you can look at the internet today, and you can see, big address blocks being assigned to HP and Stanford and MIT. They got /8 networks, got 16 million IP addresses. Nobody would argue that they weren't isolated. No one would argue that they weren't multi-tenant or secure. So basically, cloud-native networks follows that very same paradigm that we see on the public internet today, where basically you take a tenant and you give them a static block of IP addresses, contiguous IP addresses, okay? So that's, we build the isolation mechanism right into the IP address. And literally what I mean by that is we put a tenant identifier and a network segment identifier and the endpoint ID right in the IP address itself. So we embed that information right in the IP address, and then once we've done that, we can rely upon all the existing layer 3 infrastructure to get the job done, whether it be isolation, routing, filtering, quality of service. Everything that's been built in the physical network today works at layer 3 on the physical IP address, and all those capabilities are brought forward into this new approach. So it requires nothing more than standard layer 3 routing, and importantly, as data centers are designed today, they use a hierarchical routing design to take advantage of route aggregation, again, to simplify the configuration of these devices. And again, the bottom line here is that if you take this approach, the virtual networks disappear, and all the complexity that goes along with that disappears, and you regain the performance that you were devoting to the virtual networks and the visibility and the control that comes with just managing the physical network. So click forward, Robert, please. So, as I said, the complexity really just melts away. No VLANs, no VXLANs, no tunnel endpoints, no VNIDs, no OpenFlow, OpenSDB, OVN, a lot goes on and on and on. That's just part of the list of things you've got to deal with when you've got to build these overlay networks. It just doesn't exist. You don't need it anymore because we provide those capabilities at layer 3. Now, again, I talked about using the route aggregation of the spine leaf architectures and so forth. And what that also allows us to do is to eliminate the additional problem of distributing routes among the server endpoints. So by exploiting route aggregation, we can also eliminate the route distribution mechanisms that are typically used with automated virtual network solutions like BGP or XMPP or even key value stores. So anyway, the bottom line here also, ultimately this is going to simplify operations tremendously. Robert, can you click forward to the next slide? Okay, so how does this work? Let's drill down into some more gory details. Oh, there's Robert.
Sorry.
It's okay. The way this works is, as I said, we provide a tenant identifier and a segment identifier and a host endpoint and put that in the actual IP address. And what that literally means is that we assign a CIDR length for each physical host or node. Then within that range, we give each tenant a longer CIDR address. And then for that tenant, we provide segment CIDRs that are even longer. So basically, we nest the address hierarchy. So we have physical nodes, tenants, and then segments, and then endpoints, all within that natural address hierarchy. So what this literally means is that on every host, every tenant gets an actual physical network. And the tenant can, at that point, take that physical network and divide it and subnet it however they feel necessary. Okay, so that's the strategy for building cloud-native networks. Now, in order to do that, we built a solution that automates and provisions these networks automatically. And the trick here is that when you bring up a new endpoint, container or virtual machine or something, you have to make sure that it gets an IP address that conforms to this whole system. So the intelligence here is actually in the IP address management. Intelligence is in the IP address management. So you can really, I kind of think of this whole problem as we've kind of turned the reachability problem inside out and turned it into a IP address management problem. So we have an IP address management system to maintain this address hierarchy, and then we can apply layer 3 firewall rules to maintain that isolation on the host. So click forward, Robert. Okay, so here's a very specific example. Here's a v4 address, and just for simplicity, I've identified 8 bits to identify the host, the physical host, 8 bits to identify the tenant identifier, and then 4 bits and 4 bits to identify the segment ID and the endpoint ID. So literally what that means is, here's an example. On host 1, host 2, and host 3, the host gets a /16 network. So each of these hosts gets its own physical CIDR block, and the address is going to be .1, .2, and .3 for these hosts. And then within this host, I can identify a tenant. So here's tenant 1. So they get 8 bits, so they're going to get that next octet. So tenant 1 on host 1 is going to get 10.1.1.24. Likewise, on tenant on host 2, it's going to get 10.2.1.24, and so on and so on. And a segment within that network, say we identified 4 bits for that, so that's going to be a /28 network, and if we set the segment ID 1, that's going to flip that bit in the 28th position, and the CIDR for that segment on tenant 1 on host 1 is going to be 10.1.1.16. And that's how it works. And then when an endpoint is scheduled for that node on that segment by that tenant, our IP address management system is going to compute an endpoint ID and assign this address that maintains this hierarchy. So in this case, I've got pod 1 with an endpoint with an ID of 11. The IP address is going to be 10.1.1.27. I went through that really fast. I'm sorry, it's just in the interest of time, I really had to roar through that. But there are there's examples there. These numbers do work out. So let's go to the next slide. So physically, what this means is, here I've got a host. This is the Linux kernel. This is routing inside Linux kernel. We don't do anything there. And then here's a pair of pods that have been set up. The pink is one tenant. The blue is a different tenant. And then you can see that on host 1, all these are going to have host number 1 in the first. It's actually the second octet. And then tenant 1 is going to have a 1 here. Tenant 2 is going to have, tenant 2 is going to have, if the numbers do work out. My point is that this is the assignment for the individual endpoints that are set on the host. And then this allows us, we don't have to do any route distribution. So another big problem with SDN solutions is when you add a new endpoint here, you've got to inform all the other hosts with information about how to get to that. That's the whole route distribution problem, or the VNID problem. When you exploit this route hierarchy and route aggregation, the only thing you need to do is bring up this interface, and you're done. Because all the routing is static inside the physical network. Not only on the physical network, but also on these hosts as well. So again, the complexity just dissolves. Okay, Robert. Okay, so all this is built in a new open source project called Romana, and it's we call it Cloud Native SDN. All the details I talked about tonight are there in sort of gory detail. So I invite you to go take a look at that. It's all open source. It's all Go. GitHub, github.com/Romana. We announced this last Monday, we're up to release version 6 that's integrated with OpenStack. And the Kubernetes integration is not yet done yet, but Robert will show you a live demo of our efforts to build multi-tenancy and policy-based networking into Kubernetes with that. So click forward, Robert. This is where my expertise sort of fails me. I think everybody in the room here knows more about Kubernetes than me, but let me try to walk through with you how this is actually going to work. And Tim, maybe you can fill in my gaps where I stumble. So the way the third-party resources are used to allow back-end systems like Romana to be configured with the creation of new pods, services, and endpoints. So this begins by applying a network policy schema, which is a third-party resource, to the Kubernetes master. And what that's going to do is create an API endpoint that can be used by the back-end third-party system, in this case Romana, to watch for activity for those particular types of third-party resources. So that's done up front. And then you would apply a network policy instance to Kubernetes, and then you launch your endpoints and service and what have you. And then when that activity occurs, we are watching it, Romana is watching it, and that triggers the creation, the calculation of the IP address, and initiates the assignment of that address to the interface on the scheduled node. And that is done through a local agent that we've built, in addition to a container network interface plugin that we've built as well. So this is kind of generally the workflow. I hope I didn't butcher that process. Or maybe somebody can correct me where I've gone horribly wrong on that. But generally speaking, that's kind of the workflow of what's taking place. Next slide, Robert. So here are some examples. Robert might be able to show this live as he goes through the demo. But here's an example of a network policy resource. This is a schema that is still in a state of pretty high flux. What you see here is the API endpoint that I described. It's a third-party resource of type of name network policy, and it's going to again create this new API endpoint. Go to the next slide. So the demo that we're going to show is going to have two different pod specifications for a front end and a back end, and it's going to use a label. We haven't quite built all the details of this that would allow us to use namespaces to establish multi-tenancy. But in this case, we just use a very simple label to identify the owner. Here is tier one. I'm sorry, tenant one. So this is a tenant that shares two tiers, and we give them the tiers a label front end and back end. So click forward, Robert. And then here's the policy itself. So here's an example of a policy that can be applied to those endpoints when the selector matches the label. And in this case, we're going to specify the relationship between the front end. Here's the front end here.
That's the replication.
Oh, that's the replication. I'm sorry. Here we go. Okay, here we go. Yeah. So here's the policy specification where we allow traffic from the front end to reach the back end. And just in the interest of time, I'm going to just click forward to that. So click forward to the next one. Okay, so here's an example of that. This is what you're going to see in the demo. We're going to launch a replication controller that launches 3 pods on tenant 1, and then a front-end pod and a back-end pod on tenant 2. And then what you're going to see is the fact that when we launch these pods for tenant 1 on these 2 different tiers, front end and back end, you'll see that they can't communicate with one another. Then we'll apply the network policy, then they will be able to communicate with each other. Then we'll delete that network policy, in which case they will no longer be able to communicate with one another. So that's the demo you're going to see, and it works like that. Okay, Robert, next.
So will it kill existing connections when you delete the policy?
Yeah, absolutely.
So it's just not.
Okay, so I've already gone through what the demo is going to look like, and I think that's my last slide, and I'm going to pass it off to Robert now.
Okay. Now the fun is how do I think I'm just going to do it from here. If
I don't mind.
Yeah.
If you need that.
Yeah. YouTube probably can't hear much.
You need to speak into this one
I
here.
need to speak into this one. Okay. I'll try to be as loud as I can be. Let's see here. So
Why don't you just put the microphone down so you can use 2 hands. So let me tell a little bit about what we're showing. In Amazon, we've got 2 EC2 instances running Kubernetes nodes. One of them is the Kubernetes master, and on that master is being run all of the Romana processes, all the ones you saw on that slide. We've got a route controller, we've got a tenant manager, and policy manager, and so on and so forth. So, Robert?
Yep.
All yours.
So this doesn't stop sharing.
Question.
Yeah.
Where is your APIs hosted? Are you hosted out of the cloud or are you hosted within the infrastructure that you're building?
You can you run our software locally, so the APIs would be running on server that's running.
Hello. Okay, so what I'm going to do first, I'm going to log into one of the two nodes, which is going to end up running we're already running the master services. If we just sort of look through, you can see the Kubernetes services. This agent is the agent that Chris was talking about that's providing the interface into the CNI interface from the IPAM engine. So those services are running locally. What we were going to do is create a couple of these resources. So first we can see that we have two machines. And I am nowhere as slick as Tim at doing this. There's no question about it. All right, so we have two nodes. We have the initial node here is the one that's also running our master service. The second one is just a slave. So we have the two different devices. And then again, what we're going to do is first we have a little script to pull a little bit more of the information out of the get pods result. There's nothing there yet, so we're going to create the two pods. Unless people really want to see it, I'm not going to create the replication controller version, which just creates 3 different entities. So we're just going to create 2 pods, specifically a front-end pod. And so we have that guy created. All right, now if I look for the pods, I see that I have a running pod. It's running on one of my nodes, and so we'll be able to hopefully see that we have a pod on each of the 2 different nodes running. We got an IP, and as Chris was going through this, right, so the second octet is the tenant or owner, so it's 1 level of segregation.
That's the host.
That's the host, sorry. The second, the 18 is the tenant, so that's a level of segregation. And then the .3 means that we sit in the first segment, so the zero segment, and is one of the addresses that was delivered by IPAM for this particular pod, right? So now we have that pod addressed. Just for completeness, we can look at the pod definition again. So here again, we said we're going to create an owner, so 1 tenant. So these are going to both be in the same tenant and in the segment front end, all right? Now I'm going to create another resource. In this case, we're going to create the back end pod. Now we have a back-end pod. If I go and ask the system again, what pods do we have? We now have 1 on the front, and we can see that we have both different node IDs. That's good. It means we're on the different machines. And we have different host addresses. So here we have a .1 in the 3rd octet, which, as Chris was saying, in this particular example, we're using that to separate hosts at the route level. Right? We have the segment also gets broken out here. So 18 and 19 means that we're in different segments. And then the host address. I think the address allocation is different in this demo than your diagram.
Then my
yeah.
table, yes.
But anyway, so these guys are on different systems, and the first thing we can do is we can prove that we can't talk to each other. In order to do that, I need to pop into the machine. So we're going to go ahead and basically do a different way to get into the namespace of the individual entity. So here I'm on the front end. The front end has this address, so I should be able to ping myself. That works, which makes sense because that's my address, right? 10.0.18.3 is my address. What I can't do is I can't currently ping the backend node. So even though there's routing going on, I don't have access to this. I don't have access to it. Now these are both little Nginx pods, so I could also try the other way, which is really what I want to do on port 80, because I'm going to open a policy for port 80 specifically. Why don't I try to get from the front end to the back end? It probably helps if I actually do that right. Oh, nothing going, right? So we're stuck. We can't ping, we can't get there. So then what we can do, I get back out of the namespace because I want to be able to talk to the controller, and the namespace can't talk to anything, right? Or the server space can't talk to anything. So now what we're going to do is we're actually going to go ahead and create the policy. And that is here. So first we can look at the policy just so that, again, we can review this. And what we're really doing is we're saying that we're going to work on the owner tenant one, right? So that's the first level of segmentation we're going to look at. We know that we want to allow the back end to get access or to be accessed from the front end. Inverse won't work, right? So this is a one-way policy that we're going to enable here. And we're only going to allow port 80 TCP sessions to be established, right? So fairly straightforward from that perspective. In order to actually implement the policy, we're going to talk to here's the third-party API that's running on the controller. So I'm on the master, which is where the API service is running. So my API is exposed here, and again, this is the Romana IO API namespace network policy that I want to actually talk to, right? Now I have a JSON request. Let me run this policy, and we can look at, well, the JSON is that same request, right? So the system said, yeah, great, I have accepted it. Now if I jump back into the front end namespace, where was it? Do it this way. I'm back in the namespace, and again, I can ping my local address. Right? I should not be able to ping this address because I didn't open up ICMP. But I should be able to, and this is the moment of truth here. You know, I should be able to get a message from the remote device. Voila! And that's the demo.
That's it.
Right?
I could spend more time on this, but I know there's other presenters tonight. So if you have any questions, just email. Go to romana.io. There's a lot of information there. So who's next?
Mike is going to go.
Okay. I have stickers too, by the way.
I don't know if that thing is working, Mike. The other portable mouse.
It's tricky, and it's trickier than deploying other Google services. It's a little trickier than deploying maybe one of the Ooyala services. One of the main issues that we face when designing our deployment is that we have to make Kubernetes run on every single cloud that ever existed: bare metal, Tectonic, AWS, Origin, OpenShift. There's a lot of diversity in our deployment targets. So, you know, when you set out to deploy a Kubernetes cluster,
Hangout. You're not presenting on Hangout.
Sorry, got to hang out with everybody. When you set out to deploy a Kubernetes cluster, first thing you do is you pick your cloud or bare metal. Next thing you do is you pick your operating system, CoreOS or Atomic or Ubuntu. And then you see if there are any guides that match your particular matrix of configuration. And you realize that there aren't any. There are some that are sort of like it. So you start to go through all the documentation that exists and sort of fool around with things and see what works. It's a little bit painful, and we understand that. We're trying to make it better. One of the things that we're targeting, or one avenue of attack of this problem, well, I'll tell you how we got there. So basically, what do all these deployments have in common? And what are our objectives? These deployments have in common Linux. They're all running Kubernetes. Our objectives are to make deployment and upgrades robust, predictable, and easy. So one way to attack this problem is to try to run Kubernetes on Kubernetes. It's a little avant-garde, but bear with me. So our goals are to make Kubernetes deployments portable, highly available, and self-healing. So I'm going to hop into the live demos. Most of my talk is live demos. I only have 15 minutes, so I'll try to leave some time for questions. So I set up a cluster earlier today that's running Kubernetes on Kubernetes. So if I flip over to this screen, this is the new Kubernetes UI that will be shipped with v1.2. As you see here, we have the controller manager. This is one of the components of the control plane. We have a scheduler running. Each one is running with 3 pods, replicated in a deployment, which has created a You can see, as expected, I have 3 schedulers with their IPs. I also have an annotation. If you guys are familiar with Kubernetes and the Kubernetes scheduler, you'll be asking yourself, how do I have 3 schedulers running? Don't they jump on each other's feet? Well, in fact, they are using the annotation on the endpoints object to implement a very, very simple leader election. So in my leader election key, or my leader record key, in the annotation, I have a leader election record, which is serialized into JSON. And I can see that the current leader is cube scheduler LRP2 WH867. So I'm going to do something kind of dumb. I'm going to go over here. I'm going to delete that pod. So we should see some movement. The endpoint was immediately removed because obviously the process is dead. I have a release duration of 15 seconds, so after 15 seconds, somebody will hopefully hop in and assume that role. So here we go, live demo. All right, we're back. EWEFS is different than WH65 or H6Z. You just witnessed a scheduler failover. Now we have all these guys running. I'll try to tell you how I got to this point, because you can't deploy Kubernetes on Kubernetes where Kubernetes does not exist. I actually went through the process of deploying Kubernetes. The normal way for engineers at Google, we usually deploy on GCE for development. So I used the GCE kubeup scripts. I got to a point where I had the bland GCE kubeup scripts, and I SSH'd every machine. Or first, I deployed my controller manager scheduler and kubelet, and then I SSH'd every machine. I turned off the host kubelets, which caused the cluster to fail over to the kubelets that were running inside the daemon set, and I did the same with the scheduler and controller manager. So now, once we're here, how does this make life easier for the Kubernetes SRE? Well, one thing that it makes a lot easier is upgrading the cluster. Upgrading applications that are running on Kubernetes is pretty trivial. You change a field in the JSON file, you run kubectl apply or whatever your flavor is, and you let it go. So I'm going to show you an upgrade of the scheduler and controller manager right now. So over here, I have in this screen the controller manager, or the pod names that are running as the cluster components, and their corresponding Docker images. In this screen, I have the current deployments, and in the screen, I have the pods. So I'll work over here. I'm in the GitHub repository I just showed you guys. I'm using a configuration manager called, or a data templating language called JSONit. It's another Google open source project. You guys can check it out on GitHub. So what I'm going to do is I'm going to edit my env.json, which has the current versions of the Docker images that I'm running in my control plane. See mostly green. What I'm going to do is I'm going to deploy blue, controller manager, and scheduler. I'm going to generate config, which will run the JSONit commands to expand my templates. I'm going to do a git diff. And as you can see, I updated a couple labels, and I created a couple image tags inside my deployment Kubernetes object files. So what I'm going to do now is I'm going to every file in the apps directory is auto-generated. Is this font big enough for everybody? No contrast. Bad contrast. Well, I'll highlight it. So less colors, better. I have in this directory apps all my generated configuration. So I'm using the kubectl apply command. And I'm going to apply the entire directory. So now watch over on the right side. It looks like my 2 deployments have picked up that there are 2 up to date, 2 available. And as you can see up here, I'm doing a rolling update using the deployment of my control plane components. So it's going pretty quickly. There's the scheduler has one to deploy. The controller manager has almost converged, and it looks like we have converged to the configuration that I just applied. So very cool. How many of you guys have ever updated a Kubernetes cluster from a version to another version? Less of you, but it happens about every 3 months. It can be as much of a task as deploying a Kubernetes cluster. So obviously, if we could run Kubernetes on Kubernetes, it would make deployment easier. So I'm going to show you, if I have enough time, I'm going to show you the kubelet as well. The kubelet's a little different because the kubelet is running in a daemon set. A daemon set is an object that will run a single pod on every node. So it's an obvious fit for the daemon set, or for the kubelet, which is the node agent in Kubernetes. Go back into my M file. Wrong one. It looks like I updated my kubelet file. This one right here. You'll notice that I changed the name because kubelet does not have rolling updates implemented, or because daemon set does not have rolling updates implemented. I cannot use a daemon set to do a rolling update. So what I'm actually going to do is I'm going to deploy a kubelet side by side my last kubelet, which was the kubelet green running. So you're wondering what are the consequences of running two kubelets side by side? Well, not much, because I put at the very beginning of the kubelet main a file lock. So every kubelet has to acquire a file lock before they start their sync loop. And if you could read the bottom, it says acquiring lock on var run lock kubelet dot lock. So no consequences of running multiple kubelets on a single machine. So what happens when I delete my old kubelet deployment or kubelet daemon set? So right now I'm deleting the kubelet green daemon set. So as you can see, now I'm running an entirely blue cluster. So upgrade complete. If I go and tail the logs of the new kubelet, as you can see, the kubelet sync loop started, the handoff was successful, and I have a fully functioning green cluster. So git status, git commit like a good Git citizen, because I version all my configuration in source control, so I know exactly where I was at any given point in time. And so what happens when I want to roll back? Well, it's really simple now. I know it's a problem with the new version of Kubernetes because Kubernetes is full of bugs. What I can do is, as an SRE, I can revert my configuration, revert work in progress, and run kube control apply again. And now we have just deployed green again. So we did a hopefully successful rollback to green. So yeah, as you can see, it's coming along. It takes about 30 seconds to do a full upgrade of Kubernetes. So this is great. What have we solved? Well, we have made high availability. We have made a highly available Kubernetes cluster. It might be a little worse in some ways than running Kubernetes master components on separate nodes, but it actually is an improvement in other ways. So the trade-off is up to you. We've made it very easy to upgrade Kubernetes. So if you upgrade Kubernetes often, this might be an option for you. This is very experimental. We're working on making this the default setup if people in the community decide this is a good way to run. So back to the presentation. We have a Slack channel where we discuss these cool things that we're trying to do with Kubernetes deployment. It's called SIG High Availability Group. It's the you can get an invite. The invite is open. If you go to slack.cadis.io. We also have a mailing list on Google Groups. So come join us. We haven't had our first meeting yet. We just created it a week or two ago.
I had a question about, so you can't, like, can you schedule pods while this is all going on, or like, no, right?
Yes, absolutely. So
it's,
yeah, this is actually a fully functioning cluster. I can run Nginx, and it'll just start up. And as you're doing the upgrade,
Right.
these components should stay available. A couple Nginx pods popped up at the bottom there. These components should stay available if you have services running them. The services should remain responsive. Question?
So I noticed that you use the Fluent as
Yeah.
is there any particular reason why you
Can you repeat the question?
compared to like Kafka?
So FluentD is actually only used as our node agent, and it was picked a very long time ago as the default. In GCE or in GKE, we actually run FluentD on nodes and we ship it to Google Cloud Logging. What we wanted to do for every feature that we created in GKE that ties into Google proprietary services, we wanted to duplicate that with some open source projects, like, for example, the Elk stack, which is Elastic Logging and Kibana. We have the exact same thing with FluentD shipping to Elasticsearch for open source. So to answer your question, circle back. We wanted to have a reference implementation for something as useful and as necessary as shipping container logs. And we just picked it. We don't really have that much experience. If you like the competitors, feel free to use those and send us the JSON.
In the future, actually, can use it.
Yeah, you can use anything. The FluentD is just tailing a log file in Marlin Docker, pretty much. Any other questions?
Did you have to make any?
Yeah, go for it.
Did you have to make any changes to the kubelet to run 2 copies, or?
There are 0 patches in my build of Kubernetes. So everything here, if you look at the kubelet v1.2 or the scheduler v1.2 help, we have the leader election flags, so you can set all those yourself. The feature that I was using on the kubelet, there will be a lock file flag on the kubelet in v1.2 kubelets. So stock Kubernetes cluster. Any other questions? Okay, I will yield.
Awesome. Thank you, Mike. And you also have to use this. You use this. I'll try to find a charger while you're speaking.
Okay.
You need to go back to your desktop. Go back to your desktop screen, and then there's a thing that you need to install. Go to Finder, click to share, and double click on click to share. And you should be ready to go in a second. Yeah.
I can just
You're
use
sharing now. You can use either mic. Which
Yeah, I'll
one?
just use mic.
Just use this one. Are you presenting your sharing screen?
Yeah.
Okay. Here you go.
So I.
And you are unmuted, right? Check the mic as well.
Hi, can you see?
Yeah, hear me? Yeah.
Speak up, take over. Hello, everyone. My name is Xiang. Hey, everybody. Hey, everyone, one more speaker, please. Hello, everyone. My name is Xiang. I work at CoreOS. I work on SAD for most of the time, and I also work on Kubernetes, improving the scalability of Kubernetes. So today I'm going to talk about SAD, and I'm going to talk about how Kubernetes uses SAD, and how we are improving SAD to make Kubernetes better. So first, I'm going to give a very high-level introduction to SAD. So from very high level, SAD is very simple. It's just a key value store. So user can put keys into SAD, and then user can get value out of SAD. Different from other key value store, SAD is also replicated. It's also highly available, and it's consistent. SAD is fully replicated, which means a user can set a key into SAD, and then the SAD node will replicate the key to all its peers. So in this example, we have 4 nodes. So once a user put key like foo equals 5, it will replicate all its peers. Or once the majority of the nodes get the updates, SAD can actually commit the writes and return the response to the user. And also SAD is highly available. As long as the majority of the nodes inside the cluster is available, SAD will become available. So in this example, there are 5 nodes. If you lose one node, SAD is still available from the external point of view. If you lose another one, it doesn't matter, SAD will still be available. And when you lose the third one, SAD will not be available, and user cannot run more keys into SAD. But in this situation, like you still can recover SAD from this failure. You can recover a node, and SAD will become available automatically. And if all the 3 nodes are gone permanently, you still can recover SAD by taking the data from the existing node to another like machine, and then you can rebuild the cluster from scratch. So SAD is also consistent. This is very important for the client because the client can build the entire cluster as a coherent unit. They can write keys to any of the nodes inside the cluster. They don't need to care about like which node I'm talking to. So once they get the key committed, they can get the key back from any of the nodes from the cluster. So that can simplify the client logic a lot. So that's basically what SAD is. And Kubernetes uses SAD as a workflow storage. It stores all its configuration data into SAD, and it uses SAD to do the coordination work between all the components inside Kubernetes. So only the API server inside Kubernetes talks to SAD. Other components will talk to API server, and the API server will redirect that request to SAD and use SAD to do the coordination. So for the configuration part, there are 2 things. One is node. So Kubernetes store all the node information into SAD. For example, like what's compatibility of the node, how much memory a node has, and how much CPU a node has, and also like store its description, like what's the name of the node, what the OS the node is running on, and also it stores all the like port information into SAD. Like what's the ports information? Is it just created and waiting to be scheduled, or it has already been scheduled? And it also like store the like requirements of the ports into SAD. For example, like how much memory this port needs to run, and how. Yeah, I know. Is there a charger?
I don't have one.
Yeah, I think it can still like last for a while.
my talk is short.
It's for Mac.
Yeah, I think that should. Thank you.
And Kubernetes also uses SAD for coordination. There are two parts. The first part is push updates. For example, like when the user create a port, can submit port to Kubernetes. Kubernetes will use SAD to push that updates to the scheduler, and then the scheduler, knows, okay, here's the port I need to schedule. And once the port is scheduled, Kubernetes also uses SAD to push that update that the node is scheduled, and then the node will try to download those containers that port needs and start those containers. And also, Kubernetes uses SAD to implement its leader election API. So with that API, the applications running on top of Kubernetes can easily implement high availability features because they can easily select stable leader. So SAD is a pretty young project. It's only like 2 years old, and we are still making a lot of progress on SAD. For example, Kubernetes today runs well on SAD because the scalability goal of Kubernetes is just like several hundreds of nodes and maybe some thousands of ports. But we are going to like push forward the scalability part of Kubernetes. We won't have a very large Kubernetes cluster, like for maybe like several thousand nodes and hundreds of thousands of ports that requires SAD to become even more scalable. And also, we want to make SAD to support more reliable watch feature. So I mentioned that SAD support watch. So so the application has watch on key inside SAD, and if there is an update of that key, SAD can broadcast these updates to the application. If the application runs well and the network connection between the application and SAD works well, this feature will work well. But when there is a network problem or the application fails, SAD may not be able to deliver those updates very reliably because SAD only keeps a very short history of those updates. So if your application fails for a long time, SAD may not be able to redeliver all of the updates. You may do some updates. So that requires the application to handle this failure case, and this makes the application logic really complicated. And we want to solve that by making SAD even more history and make that more reliable. Also, SAD wants to support multiple key transactions, which means in one request you can modify multiple keys atomically. So, if this can reduce the latency when you do bulk updates, and this can greatly simplify the application logic, because right now the application needs to do multiple concurrent work to make sure all the updates are committed in an atomic fashion. And when we have this multiple key transaction, it can greatly simplify the application logic. So we are working on a new version of SAD. It's called SAD 3. So it has a very simple key value API, and it supports mini transaction over multiple keys, and it also supports multiple version key, and it supports a more reliable watch, and it uses memory much more efficiently. So for the key API, it's very simple. SAD only supports a binary key space, so you can put a key, you can get a key, or you can range over a key space. You can delete a key, and you can delete a range of keys. And as I mentioned, SAD support something called mini transaction. This is actually very simple. It looks very like the if statement. So when you want to construct a transaction, you first fill in the if statement. So just some compare statements. So you can compare a value of a key, you can compare a version of a key, and if that all the compare succeeds, we will go to the then statement. So in the then statement, you can do multiple operations like put a key or delete a key. And if that compare fails, it will go to the else statement. So in the else statement, you can have multiple operations, and this transaction will be committed atomically. So that's a mini transaction support in SAD 3. SCD3 support a feature called multi-version key. So you can access the past versions of a key. So in this example, we put key full 3 times. So first we set it to bar and then bar 1 and then bar 2. And when you want to access the value of full, you can specify a reversion, so you can get access to the previous version of key. This is important when the application wants to implement automatic concurrent structure, or like the application wants to have a consistent snapshot of SCD, because like when you put more keys, you will not override the version of key you want to access. Also, as mentioned, like SCD3 support a very reliable watch feature. So in the client library, you can just do a watch, and SCD will handle all the failure case in the backend for you. So there are some work we have done in the client side, and also some work we have done in the server side. So mostly, like the server keeps a much more longer history for specific clients. The client actually catch up when it fails, after it fails, so it can help agent to recover more effectively. Also, to support millions of keys, SCD needs to use memory and CPU more effectively. So in the V3, we observe like 8-time memory consumption reduction compared to SCD2. And I mentioned like there's a watch feature in SCD2, like when the application wants to watch on key, it needs to have a dedicated TCP and HTTP connection. That uses a lot of resources when you want to watch multiple keys in one application. And in SCD3, we try to like share one like TCP and HTTP connections as much as possible. So in one application, you can have one TCP connection.
Yeah, so every connection you're trying to use gRPC.
Yes.
HTTP.
Yeah, we are using gRPC to do that because HTTP supports like multiple streams on one connection. And we also move the in-memory storage off heap because we don't want to pay a lot of cost to the DC. So that helps DC a lot when you have a really large in-memory state. So we are working on SCD3. Most of the features are finished, and we are in the final testing stage. And hopefully, we can release SCD3 late Q1 or maybe early Q2. And for the Kubernetes part, we are working on a proof of concept of SCD3 Kubernetes integration, and hopefully we can share this work after a few weeks. So that's it. Thanks. And we are hiring for.
Thank you, Xiang. That was awesome. We can't wait for the integration to be completed. You have questions, Brian?
In the previous slide you mentioned there is an 8x performance increase. Have you done testing with that, or are there data from it?
We have some internal performance testing, like compared to SCD2, and we will release the results after a few weeks.
Okay.
When you talk about this supporting Kubernetes of 10K nodes or plus, do you expect that can be achieved on a single node, or has to be a large cluster SCD?
So actually, like SCD usually